welcome to polar versus nonpolar bonds. What it means to be polar is to be different on your ends. Two common examples of some things that are polar would be the Earth or would be magnets. The North Pole of the Earth has polar bears, whereas the South Pole has penguins. It's different. A magnet actually is a North and South Pole, which have different pole and different properties. So when something has an element of asymmetry to it, that is going to lead to what we call polarity. In order for something to be nonpolar, it has to have an overall balance or symmetry to it. So symmetry has to do with nonpolar. Asymmetry has to do with polar. Those can be very easy to get backwards. A polar bond, and when I talk about a polar bond, it's different from a polar molecule, is an unequal sharing of electrons between two different nonmetals. Those two nonmetals are going to have an electronegativity difference meaning because they're not identical to one another, their electronegativities are different. They are not pulling on electrons equally. That difference is usually fairly low, less than 1.7, but there will be a difference there. They're not going to be two atoms with the same electronegativity. Polar bonds are different from polar molecules, and I will show you a slide in a minute where I contrast this a little bit more. Nonpolar covalent bonds are a completely even sharing of electrons. These bonds occur between two identical atoms of the same element. So the atoms are sharing electrons completely evenly. If we look at Cl2, for example, each of these chlorines has an electronegativity of 3.2. And electronegativity is telling how strongly these two chlorines are pulling on electrons. Neither one of those electrons is pulling on, or neither one of those atoms pulls on electrons more. So in this bond, neither atom exerts a greater force on the electrons between them. This is like an even tug of war, and this is true with any diatomic. So in a nonpolar bond, your electronegativity difference is 0. And this does happen to also be an example of a nonpolar molecule. But I'd like to take a minute to kind of compare and contrast the bonds and the molecules and polar, nonpolar, and all that stuff with a few examples. So this first molecule I have right here is F2. Each of these F's has an electronegativity of 4.0. Therefore, this bond right here is a nonpolar bond. If I asked you your molecular polarity, you would do a chop-chop test. Chop, 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 symmetrical. Chop, 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 symmetrical. This is also a nonpolar molecule. Now, if I swapped out one of those H's for, or one of those F's for an H's, or an H, sorry, all of a sudden this changes things quite a bit for me. So my electronegativity for fluorine is 4.0. However, my electronegativity for hydrogen is only 2.2. What this actually means is fluorine is actually pulling electrons towards itself in an uneven fashion. Hydrogen's not as good at holding on to electrons as fluorine is. So what this causes is a polar bond. Then if I wanted to look at my molecule as a whole, I would again do chop-chop. I am symmetrical this way, but I'm not symmetrical this way, which means this is a polar molecule. It is different on its ends. It's a little bit negative here and a little bit positive here. Whereas in the F2 molecule, charge was very evenly distributed throughout the entire molecule. So I like these two examples down here. These kind of give us an even better way to compare and contrast these ideas. If we look at methane, which is CH4, our carbon in the middle has an electronegativity of 2.6, and each of these hydrogens have an electronegativity of 2.2. These bonds are all polar. They're between two different things that pull on electrons with different force. However, chop, 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 we got a whole lot of symmetry there. So this is actually a nonpolar molecule. So just because you have polar bonds doesn't mean that you're going to have a polar molecule. The overall charge distribution in this particular molecule is very symmetric. Symmetric charge distribution leads you to a nonpolar molecule. Now, I did want to show you one example of a molecule where you can actually have a nonpolar bond that's not diatomic. So we have 2.6 here, 2.6 here. This bond is nonpolar. However, these bonds right here are still polar. So if we were to actually go chop this thing, we notice it's still symmetrical overall, and we still have a nonpolar molecule. So when you're talking about the molecule overall, you're talking about looking at its overall charge distribution as opposed to just focusing on one individual bond and how the electrons are shared within that individual bond. Sometimes we like to kind of show electron clouds to make this a little bit more visible. Polar molecules, if you're going to have one of them that's pulling the electrons more closely towards itself. So hydrogen's electrons get pulled toward chlorine. Chlorine's also got these lone pairs out here. So if we actually want to draw a little cloud showing where there was a bigger density of electrons, that would be occurring around chlorine. Chlorine does have this little bit of a negative charge out here. Hydrogen's electrons are pulled away from it, so it's a little bit positive. So that's a polar molecule. It also has a polar bond in it. This is polar right here, because those are two different things. Water is another great example. We have a big difference in electronegativity. These bonds right here, polar. The molecule as a whole is also polar because we have a big, bulky electron cloud causing asymmetry around oxygen. In a nonpolar molecule, like CO2, for example, what actually happens in CO2 is electrons are getting pulled out toward the oxygens because they have a higher electronegativity. They also have lone pairs, so you actually get a big, bulky kind of dumbbell-looking thing where you still have that symmetric distribution of charge overall. Like if you chop this, symmetry, but you kind of have your electron cloud sort of pulled out to the edges. However, this is still a nonpolar molecule, even though it's got these polar bonds, because overall it has charge symmetry. Another way of talking about polarity is the term ionic character in a bond. Ionic character is how much like an ionic bond a bond is. In other words, how unevenly are electrons being shared, or are they being transferred even? And this is measured by electronegativity difference. This will describe how unevenly electrons are being shared. These are not values that you need to know. What you do need to know is a higher electronegativity difference will give you the greatest ionic character. So these are just some examples. This table starts by showing you a nonpolar covalent bond which has no ionic character at all. That's the opposite of ionic character, because ions are when we transfer electrons. So completely even sharing is different than that. So that's what you're going to see in a bond between two identical elements. Then we have moderately and more polar covalent bonds. So these are when you're same side of the staircase, you have two nonmetals, but you do have an electronegativity difference. So you have two non-identical nonmetals. And then finally, we have our most ionic character, which is an actual ionic bond, which remember, we're actually transferring electrons there. So that's when we're going to have a metal and a nonmetal, because the metal's losing electrons to the nonmetal. So if a question is asking you about degree of ionic character, what you're really looking for is a high versus low electronegativity difference. If the question wants to know which one is the most ionic character, you want the highest electronegativity difference. If the question wants to know which one is the lowest ionic character, you want the least electronegativity difference. So that's kind of what they're getting at when they ask you a question like that. You'll not be asked to categorize them the way that they're specifically listed on this table. We're just going to wrap up your, actually we're going to stop there.